Welcome back to the lecture on convex optimization, and we are on the last leg of our lecture. So, we are covering a very important area and very hot area of convex optimization called semi definite programming. We are obviously not going to cover each and everything that is there in this vast and beautiful subject, but we are going to touch on some main things like optimality, duality, and we are going to also mention the major results rather than getting into details, and we will provide some examples and give a brief idea of how interior point methods can be developed for them. So, this is in general our plan for semi definite programming, and we will show that many important and interesting problems can be posed as a semi definite programming problem, and SDP can be actually solved out. So, here is a semi definite programming problem as we have seen in the last class, and where Sn is the space of symmetric matrices and the inner product is nothing but trace of x y, and this would lead us to define a problem which looks almost like a linear programming problem in matrices. But since Sn plus is not polyhedral as we had discussed, this is not exactly a linear programming problem in matrices, but a convex programming problem in matrices. So, basically you are solving a linear matrix function over a convex set in Sn plus rather. So, if you look at this expression, this constraints a I x equal to b I, let me consider the following linear operator. The following linear operator A, which takes an Sn and gets puts in Rm. So, it is A of x So, if I look at this, then what is my semi definite programming problem? If you look at this, I can write this also as so EI you know is the vector whose ith position is 1 and rest are 0. Now, once I know this, I can write my SDP problem as to minimize Cx subject to the linear operator Ax equal to b, while x is in Sn plus. Now, this A being a linear operator, this is A, this A is a linear operator. This is a linear operator. So, we can define the adjoint to this operator A star this is obviously this adjoint operator is unique. So, which is defined as follows. So, this inner product Ax is in Rm is same as A star y. So, A star y takes an element in Rm and maps it in Sn, and that you. So, this is nothing but trace of A star y x, this thing. So, they here through this adjoint we are linking the ordinary dot product in finite dimensional spaces with the dot product of or the inner product of the space Sn. Now, it can be shown that A star y can be actually written as this is what A star y can be written as. This can be proved, which we do not prove. But left here as homework. Now, what is happening is, if you look at this thing, this A star y, A star is again a linear operator, because it is adjoint of another linear operator. A fundamental condition that we will use which is akin to a full rank condition in linear programming is that kernel which implies A star y equal to 0 if and only if y equal to 0, this implies summation y j a j, j is equal to 1 to m is equal to 0 and only if. Basically, AJs form a linearly independent set. Now, this result would become crucial in establishing some duality and, I would say, duality and linear optimality of this linear programming problem. So, what about the dual of this problem? That is very crucial, and dual is something which we have already shown earlier. The dual which we denote as dual of SDP is max By C minus j equal to 1 to m yj, this is element of Sn plus. So, another equivalent way of writing is, so there would be an extra semi definite positive semi definite matrix. So, I can write this as max of such that this can be written in a slightly better way. So, there is a huge amount of mimicking the standard linear programming problem, but at the end this is not really linear programming problem and needs very different techniques to solve them. Now, let us look at some selected special cases which can be converted to semi definite programming problem. For example, linear programming problem. This is actually an SDP problem. Let us look at this problem. Here you see I have not yet expressed this in the standard SDP form. What we can do, or rather show that as a homework you show that DSDP is also an SDP. DSDP is also an SDP. So, this is something I leave as homework, which will be just a little bit of fun to prove. Now, what I have not shown here is that what is the SVEC type operation. So, I will here what we will not do here, we have not shown you what is the we know what is the VEC operation of converting a matrix into a vector. So, there is something called symmetric VK which converts a symmetric matrix into a vector. We have not said anything about that, we will possibly say it later, but now let us look at the linear programming problem. So, we again have the standard LP problem, minimize subject to Ax equal to b and x greater than equal to 0. So, we will convert this to an SDP. how do we convert to SDP? That would be the case. So, now if we just said that we are going to convert this linear programming problem into an SDP problem. So, we will write C is equal to diagonal matrix of C, which is nothing but the matrix Cn, and capital X diagonal of this vector x. So, it is in this sense C of x is nothing but C1 x1 plus Cn xn, because if you multiply this vector Cx is multiply this is same as trace of Cx. So, you multiply C with x, matrix multiplication, this you will get C1 x1 C2 x2 Cn xn, and this is trace of x, but this. So, this would imply that C of x is Cx, which is there. Now, we are left to conclude about the remaining part, that is right AI is diagonal of AI. So, take the ith row of the vector and make a diagonal matrix. So, A of x would be same as A capital A of x. Capital A of x. So, basically then we will have, so capital X is element of Sn plus if and only if small x is element of Rn plus. This is capital clear when x is equal to diag x. So, this means I have been able to convert my problem. So, LP is written as so if you solve this SDB problem, with x is this, C is this, and you have actually converted a linear programming problem into a semi-definite programming problem. So, this is when quadratic optimization problems can be also converted to semi-definite programming problems, and they are very helpful in many cases. Now, I just want to mention a book by Stephen Boyd and Van der Berg. The book name of this book is Convex Optimization, published by Cambridge, and it is a very fabulous book which deals with application of SDP. Though it looks like a linear programming problem in matrices, we have already mentioned that this is nothing but a convex programming problem. It is not in general a linear programming problem in matrices. So, what would happen is that the strong duality theorem, that is the duality between this dual of SDP and the original SDP, there need not be strong duality. So, unlike linear programming, so you see there will be some little difference, strong duality would not hold. So, we are going to prove some, we are going to put some examples showing that strong duality does not hold, and this example is due to Michael Todd. A very famous optimization theorist from Cornell. So, we are going to give this example which will show that the supremum and infimum of a semi-definite programming problem and its dual, the infimum of the SDP problem and the dual, they are having two different values. So, here again we establish the claim that it is really not linear programming, because if it was linear programming, then one could have actually got strong duality. So, you minimize this. So, you can observe that these are all positive symmetric positive semi definite matrices. For example, this one, it has a greater than equal to 0 eigenvalue. Mutation matrix. So, this is Michael Todd's simple semi definite programming problem, and we are now trying to find the dual. So, the dual of SDP. So, this is my given SDP. I am writing the dual of the SDP. So, you have to maximize twice y2. You see there are two constraints. So, there will be two dual variables, number of functional constraints and the number of dual variables are always same. Just go back and have a look at the talk on Lagrangian multipliers, KKT conditions and all those things. So, here y1 a1 y2 a2, this is C minus summation yi, this C and summation yi is element of S2 plus. So, this is something important. Now, infimum of this problem is infinite, is unbounded. So, infinity is the infimum of this problem. So, you have to figure this out. And for this problem, the supremum or the dual optimal objective value is 0. The dual optimal objective value is 0. So, there is a duality gap, you see the gap cannot be reduced unless there are certain conditions. So, we will now mention few duality results in SDP and they will be mentioned through this book, which I again want to show. This is a very useful book at the undergraduate and beginning graduate level in optimization. Now, duality theorem in SDP. So, if the dual problem has a strict feasible solution, strict feasible point, and you understand what is the meaning of strict feasible point in this case, you can translate what we have learned for linear programming, that is C minus summation yi ai should be in the int of Sn plus or Sn plus plus, that is the meaning of dual problem has a strict feasible point y. Then the minimizer of the primal point exists and the dual and primal value are same. if the primal problem has a strict feasible solution. So, in case of convex optimization, the corresponding notion is that of Slater condition. So, if the primal problem has a strict feasible point x, then a maximizer to the dual problem exists and their values are equal. These sort of results are also true in case of general convex programming problem, but the second one, for example, does really hold for the general convex programming problem. If both problems have strict feasible solution, then both have optimizer and whose value is so and so. So, if the dual has a strict feasible solution, then the primal achieves its minimum, which is very interesting, while if the primal has a strict feasible solution, the dual achieves its maximum, and that is a very interesting thing. So, if dual is strictly feasible, then a solution, the minimizer to the primal is attained, or you can guarantee the minimizer to the primal exists. That is what it says, and the dual and the primal value are same. So, if the dual is strictly feasible, then the minimizer to the primal exists and the dual and primal values are same. This is one of the first results. So, it is again you see you are talking about. So, we are again going to tell the second one, if the primal is strictly feasible and then the dual is attained and the values are same. If the primal has a strict feasible solution, that is x is element of Sn plus plus, not just in Sn plus, that is actually where the strictness comes in. If the primal has a So, if the primal has a strictly feasible solution, then the minimizer to the dual exists. Sorry, the maximizer to the dual exists, that is a mistake. So, maximizer to the dual exists and the values are equal. Maximizer to the dual exists and their values are equal. Third one we do not want to write, which says that if both have strictly possible, then both have optimizer and so forth. So, these are two very important conclusions when you look at SDP. So, it is none like a linear programming conclusion where you conclude that if both the primal and dual problem have a non-empty feasible set, then their solutions exist and basically their solutions coincide. And one has to observe that in linear programming, if both primal and dual have a feasible solution, the strong duality automatically holds. That is, if you want to detect the primal dual, if you want to detect a primal feasible point and a dual feasible point, then you are done. Then basically you know that this linear programming has a solution, which is very important. So, you just have to know this little part about semi-independent programming, not in much detail. So, now our aim is to develop KKT conditions our aim to develop KKT conditions for the SDP problem. Before we proceed to do so, let us tell that why that this strict feasibility is here. Actually, strict feasibility is corresponding to Slater condition. Now, our aim is to develop KKT conditions for the SDB problem. The question is why we need to do so. The answer is that if we can develop a KKT condition for the SDB problem, then if I can solve that KKT condition using interior point techniques, then I can solve the SDB problem. The idea is to use KKT conditions to develop interior point techniques for SDB problem. Remember, all the while this is an important class of problem with lot of applications coming in. You should see the book of Stephen Boyd to see more detailed applications, but you must be very careful that this is not a linear programming problem in matrices. So, and you get a huge literature on the net on semi-definite programming. So, idea to use the KKT conditions is to develop IP or interior point methods. So, in order to do so, we will first construct the Lagrangian function associated with the SDB problem. Lagrangian function for SDB. So, this is will denote like this, and L of x y is C of x plus summation y I b I minus a I x. So, if this is what I have, we have the following problem. So, we are first going to develop a saddle point type condition. Before we talk about a derivative in this particular case, what do I have is follows. You will see that we will be able to tell something more than general convex programming problem. So, let us do our assumptions. The assumptions are as follows. The assumption number 1 is that there exists x hat element of Sn plus plus, which is not really required, which is true. So, there could always be an element in Sn plus plus such that A of x hat is equal to B. Number 2, kernel of A star is equal to 0 vector. So, once you have this, we can prove that there exists a y bar element of minus Sn plus such that L of x bar y bar. So, of course, we have assumed that x bar is a solution of SDP, that this now this being some sort of a linear function again in the set space of matrices. So, here we have in general the y bar there exists y bar element of Sn plus and I forgot to tell you an y bar element of Rm, because this Lagrange multiplier associated with equality constants will not have a sign. So, there would exist these two quantities such that this will be true and x bar y bar, this is an additional information, is equal to 0. Now, what does it show? That L of x bar y bar is equal to the conditions. I can now write them into this equivalent form: minimum over all x element of Sn plus L capital X y bar. This is what you have, and subject to x bar S bar is equal to 0, where S bar is equal to minus capital Y bar is element of Sn plus. I can write it like this. Now, the first condition, obviously this Lagrangian is differentiable in linear, you would have gradient of x of L x bar y bar is equal to 0. So, if you have the gradient of that, then it will become C. If you look at the gradient again, so it will be C plus, you are taking a gradient with respect to x. So, basically it will become C, you have to do yi bi, and this will get into summation yi ai. So, basically what you will have is C minus summation yi ai. So, if you take the gradient, this is what is coming, and obviously x bar has to satisfy so this, and you also have x bar S bar is equal to 0. So, this condition, this can be written as C minus, no, this cannot be exactly equal to 0, it is element of Sn plus. So, I would ask you to figure out, now this cannot be grad x equal to 0, it should be grad x is element to normal cone to Sn plus at x bar, the negative of this, the negative of the gradient is this. So, normal cone is minus Sn plus, so it will become minus C plus this. So, it will become C minus A star y, this is now element of Sn plus, and A x bar is equal to B, and we have this additional condition, we can x bar S bar equal to 0, but what is my, and also I have this additional condition that x bar and S bar is equal to 0. Now, how do I prove that this is actually equal to S bar? So, my problem would be solved if I can show that this is exactly S bar. So, this S bar. So, if I can show this fact, then my problem actually is finished, then I have actually solved the problem. So, let us leave at this stage and ask you to think about this thing. Is this really true? And then we exactly have a similar looking KKT condition. Of course, I have not done many details, I am just writing down certain things. So, then you can form the basic conditions. Now, you observe that this is what you will have, and the normal cone here is nothing but Sn plus, a thing which one might not able to understand. So, those who are not very mathematically involved do not get too much bogged up with this particular issue. So, why x bar into s bar would become 0, or whether is this true? This is the question I want to ask, and tomorrow in the next class we will address this question. I will end for the day.